Hello everyone. As you know, we have already started a series of lectures, and you know that very important topic that Fresnel biprism and Newton rings are completed. So third very important topic that is known as Michelson Interferometer. Who was Michelson and what is interferometer? Actually, full name of the Michelson is the Albert A. Michelson. Was born in Germany and come to United States age of 2 with his parents. And the most contributed part of the Michelson is the Michelson-Morley experiment, that collaborative work. So let us understand the concept of that. Michelson is the name of scientist. Interferometer is a device. In that device, discovered by Albert A. Michelson. So what is the role of this? That how to find many important applications. Now understand this diagram. Now this is the simplified diagram of the Michelson interferometer. This is any source. This source is sodium light source, maybe any other source. So this source ray may not parallel. So how to make parallel ray? We put a lens which is placed focus of this lens. After that rays become parallel. So parallel rays incident on the glass plate, which are special glass plate which is known as beam splitter, and this plate is inclined at 45 degree toward the incident light. This is 45 degree angle. So this is 90 degree. This is 90 degree towards that mirror M1, and this is there another mirror M2. There are two mirrors M1 and M2. The first mirror M1 is called movable mirror, that can move through the screw, and because screws are there on the back side, and this is called fixed mirror. So there are two glass plates, G1 and G2. G1 glass plate is semi-silvered glass plate. The role of this glass plate is to divide the incident beam into two parts. Now the first part going towards that mirror M1, and other part through this transmitted light, it is deviated through some part and going towards mirror M2. Now because mirrors, they have reflection, they are polished backside, so rays can come to again and recombine at the point A. So remember, the distance should be equal. Distance should be equal. D is the equal distance, maybe 11. So they are diverging from point A, and after suffer reflection from mirror M1 and M2, they come toward point A, and together they come in the telescope, that is observer. So what we can see through this observer, we can obtain the fringes pattern, that may be circular, may be straight fringes. So how the rings are formed, because image of M2 is also formed at M1, that is M2 dash. So the previous two topics, Newton rings and the Fresnel biprism. As you know, in the Fresnel biprism, we get straight fringes. Fresnel biprism, we get straight fringes. I mean, this type fringes we get, straight pattern we get in the Fresnel. And in the Newton's ring, we get the circular fringes like this. Circular fringes, we get this. But in the third type, that is Michelson interferometer, we get both. We can obtain both circular as well as elliptical. I mean, we can obtain the circular, we can obtain this elliptical, I mean straight fringes. So especially now one can ask the formula that already we have covered in this, that the lambda equal to beta into 2d by capital D. This is formula. Okay, in this case lambda equal to dnp square minus dn square upon 4pr. Okay, now in this we will learn formula lambda equal to 2x by n. Now one can ask the question, what is the role of the Michelson interferometer? Already we have covered that lambda is covered through this formula. I mean, suppose there is a source, the common source, sodium light source. We will obtain same wavelength through this formula and same wavelength through this formula, and also the same wavelength through this formula. So what is the difference? Difference is that this Michelson is more accurate and that is more facilitated other than 2, because we get both circular as well as straight fringes. So we will learn about that, how it works. When from source light passes and going towards that the plate, this given plate, glass plate, and this glass plate is semi-silver backside. So what is the role of this plate? To split the ray in 2 parts. One part is going towards that C, and other part is going toward AB. Okay, the specialty of this plate is to divide the incoming beam into 2 parts, because they suffer back reflection from the back of the mirror M1, M2. They recombine at the same point and coming together in the telescope. Now one can ask the question, what is the role of this another plate G2? G2 is called compensating plate. You know what is meaning compensating plate? Because somehow the path is not equal between the A and C and A and B. So just to equalize the path difference, we add a simple glass plate, that is G2. Now this plate is different from this plate. This plate is the semi-silver backside, this is ordinary glass plate. So the role of this plate is the only to compensate or to equalize the path difference, so that we can get the fringes pattern. Okay, one can observe this telescope and fringes are formed toward that C point, that is mirror M1, M2, M2 dash. Now this formula can be simplified in this manner. Rays are coming from this side, from this plate, rays going towards this mirror M1, this is M1 mirror, and going towards mirror M2, this is your M2 mirror, and coming from M2, and together they can come telescope. So we will observe the fringe pattern through that instrument. Up now understand the other part of this, because one can obtain that, we can say that in the interference pattern we needed a coherent source. Can we assume that this source is coherent source? No. Coherent source means the constant phase difference. Now how to obtain that constant phase difference? Okay, so here you can observe that there is a single source. From this source 2 rays are emitted towards that mirror M1, towards the mirror M2, and they are derived from the single source, and they are in position to interfere. Okay, already I told you that single source can be produced a coherent light. I mean, there are 2 sources, they are dependent on the single source, and already we know 2 independent sources may not be coherent source, but a single source and dependent on 2 coherent sources, they may produce coherent light. So they are coming from single source, and there are 2 sources, 2 beams are created, and they are in position to interfere, and the suitable conditions the fringe pattern are observed. Okay, so now understand that application part of this Michelson Interferometer. So the first application is the how to obtain that wavelength of given source. As you know, in the previous topic we have calculated that wavelength of the sodium light. Here we can also obtain the sodium light of the wavelength of the sodium light. So application part is very important. Application part, understand the derivation part, and let us calculate some numerical problem also. Applications of MI. MI means Michelson Interferometer, short form. So the formula, that is first application to determine the wavelength of given source. Okay, source may be sodium light, very popular, or another source, sodium light. So how to obtain that? And formula that we are very easily we can obtain, that the given film is introduced one of the path of one of the interfering path, you can say. So that the formula, that is 2 mu t equal to n lambda. Okay, if the film or that spot that obtained, that is air film, for air film, and for air film we are taking generally mu equal to refractive index is 1. So this formula become 2t equal to n lambda, equation 1 you can say. Now center spot, when we put the fringe, I mean film in the one of the interfering rays, then its fringes are shifted. Okay, then again with the help of a screw we can obtain the fringes in the center position. And suppose t is thickness of that film and some distance is moved, that distance you can say t plus x the distance, and in that x distance suppose number of fringes are increased, that is equal to n plus n, small n early there may be center spot, and n number of fringes are cross the overview. So lambda is same. Now understand this. This is condition, the path difference, and this is maximum condition, n lambda. This is path difference, and mu is 1 because air film. And suppose we move, I mean when we put the film in the one of the interfering wave, the fringes are shifted. In that case, t plus x is the distance. So we can solve this. Let us say 2t plus 2x equal to n lambda plus n lambda. This is equation 3rd. Now from 3rd and 1st, from equation number 1st and 3rd, see the 1st and 3rd, we can put value here, or we can subtract 2 minus 1, 2 minus 3 minus 1, we get simply, let us write again 2t plus 2x, and this is minus 2t, and this side n lambda plus n lambda, and this is my n lambda. So see here, this will cancel out from both sides, 2 cancel out from both sides. So very easily we can get 2x equal to n lambda. Okay, so in that sense one can say कि lambda is nothing but it is your 2x upon n. So this is simplified formula. In this formula, if we know the path difference, I mean distance moved by the mirror x, and in that also we know the number of fringes moved at cross field view, so we can calculate lambda very easily with this formula. I hope this is clear. Now second application that is also very important. Sometimes there are certain sources which emit light more than one wavelength. Okay, like sodium light we have 2 wavelength. So second application part. So second application part is the how to determine the difference in wavelength. Determine a difference in wavelength. Okay, and between two neighboring lines. Sometimes we also call this how to resolve lines, resolve the spectral lines. Sometimes we call D lines, lines, or sometimes we call resolution of spectral lines. Okay, the formula that we are going to prove here, that formula is delta lambda equal to lambda square upon 2x. This is formula that we are going to prove here. Now take the example of the sodium light that produce two wavelength, that is called D lines. So D lines का मतलब होता है, D lines means lambda 1 equal to 5890 angstrom and lambda 2 equal to 5896 angstrom. So if we take average of this, average become 5893 angstrom. This is the well-known wavelength of sodium light. So there are two wavelengths, lambda 1, lambda 2. So keeping that mind, the formula that we are going to prove here again, that the power difference that is equal to n lambda 1. Okay, this is the case. We suppose there are two rings and this is lambda 1 and nearby this, very close to this, there is another wavelength called lambda 2. So from center the distance is almost same approximation. So this is one equation. The second equation is also we can write 2x equal to n plus 1, because next order of wavelength, this is 2. So now if we subtract these two, and not subtract, we can equate these two. So this from 1 and 2, ki n lambda 1 equal to n plus 1 lambda 2. So we can solve here value of n. How to find n? Because you can take n common here, n lambda 1 minus n lambda 2 equal to lambda 2. So n will be lambda 2 upon lambda 1 minus lambda 2. So we can substitute, this is equation third. So from first and third, from first and third. So first is 2x and n is your this. So in place of n, let us write again. In place of n, we can write this value. So this is lambda 2, this is lambda 1 upon lambda 1 minus lambda 2. So one can write this formula in this form, ki lambda 1 minus lambda 2 equal to lambda 2 lambda 1 upon 2x. Now remember ki if two numbers are very very close, I mean we can take the arithmetic mean. So lambda is the mean wavelength of these two. Okay, so we can put here, also we can say lambda 1 and lambda 2 nothing but it is arithmetic mean, but we can take geometric mean also, lambda square equal to lambda 1 and lambda 2. The number are very very close, so we can write here lambda square. So my formula become delta lambda, we can say equal to lambda square upon 2x. So in this case, suppose a source is emitting the two wavelength. In that two wavelength, we can find the difference in their wavelength. Like in the sodium light, difference is only 6 angstrom. So in this formula, if we know the average wavelength, if we know the part difference, we can find easily the difference in wavelength. There is another application called the how to find the refractive index or thickness of the given film. So this is a very simple formula. So what we have learned today about Michelson Interferometer, that is very similar to the Newton rings or fringe biprism, but the quality, that is the specialty, you can say application point of view, say Michelson is more suitable than Newton's and fringe biprism. We have seen that the formula looks very simple and we can find easily the desired result. So there are many applications in research also. I mean, interferometer means where two rays are interfere. So this is also used in the testing of some instruments. Like many examples are there, like in holography we know mag instrument where two rays are combined at certain point and we found the desired result.